Everybody, what we're going to look at today is energy in springs, and we want to analyze the oscillations back and forth and see what types of energy the mass spring system possess as we see these oscillations go back and forth and back and forth. So obviously the total energy of the system is going to be the sum of our kinetic and our potential energies. So we've got to look at the energy that is in the spring that's stored up when we're at our amplitudes, and our kinetic energy would be the energy of our motion when the mass starts to move. So the total energy of the system at any moment was going to be the sum of these two. And if I wanted to solve for the energy in a spring, well, that's just simply 1/2 kx squared. Now remember, our x is written as a cosine omega t plus your phase constant. So we got to sub that into our potential energy equation. And to make things even more complicated, our kinetic energy is 1/2 mv squared, and our velocity is a omega sine omega t plus the phase constant. So those two pieces have to be put into our energy equations when we're trying to find the total energy of our system. So let's set this up and see what happens. So there's my potential energy equation. I had to square my x value, so that's amplitude squared cosine squared omega t. Let's do it for the kinetic energy. So there's your kinetic energy for a spring that, or the mass that is moving through this mass spring system. So it's 1/2 m a squared omega squared sine squared omega t. Doesn't look too pretty, but one thing we do know is that the angular frequency of these oscillations, the angular frequency is just the square root of k over m. So I can put the angular frequency into here and see if I get any cancellation. So having omega squared is really just k over m, and I can get rid of my masses, and now I have my kinetic energy written as 1/2 k amplitude squared sine squared omega t. So it actually is the same formula as the potential energy equation, except it's following a sine curve versus a cosine curve. So we can find the total energy by taking the potential plus the kinetic, and I'm going to put all of the combined variables together. Like, both of them have a 1/2 k amplitude squared, which leaves behind a sine squared theta plus cosine squared theta. And if you remember from any of your trig identities, sine squared plus cosine squared actually equals 1. So that's actually really, really nice. The total energy of our system is just 1/2 k amplitude squared. So if I want to know how many joules of energy are sitting in this, let's make sure we have the units correct. The k value is in newtons per meter, and the amplitude is in meters, and we're going to square that, so we're going to get newton meters or joules of energy in our system. So let's watch this mass oscillate back and forth and identify points where there is maximum potential energy, maximum kinetic energy, and so on and so forth. So what we see here is we see a mass oscillating back and forth. It gets far away from the equilibrium point, comes back to the equilibrium point, then gets to negative amplitude. Once it's there, the spring doesn't want to be compressed, so it pushes back down, and you get this mass to oscillate back and forth and back and forth. If I wanted to analyze the energies in that oscillation, I can put on an energy graph. When I'm far from my equilibrium point here, I can see I have a lot of elastic potential energy. When I release the spring, it will go back to having no potential and all kinetic, moving as fast as possible. But then it's going to rocket right through there and go to negative amplitude and oscillate back and forth. So the energies will keep changing from potential to kinetic, back to potential again, while we look at this oscillation. So if I was going to graph my energies versus time, I can see here's my displacement curve. My displacement curve is a cosine curve starting at positive amplitude and going back and forth. So when I'm at positive amplitude, I've got all potential energy and no kinetic energy whatsoever, because all the energy is in the spring. When we reach the equilibrium point, our displacement becomes 0. That means I'm going to lose all my potential energy in the spring and gain kinetic energy. When I get back to the other amplitude, we're back to spring energy and we lose all our speed. And when we get back to equilibrium on the other side, it's just the reverse. all kinetic and no potential. So this goes back and forth a little bit faster than the oscillation for the actual mass. The energies change their forms quickly, and to calculate it, you do 1/2 k amplitude squared. That would give you all the potential energy stored up in the spring at its amplitude. If you want to know how much kinetic you have, well, they're just trading off energies. As we lose potential, we're going to gain kinetic. So if you know the energy in a spring, you actually know how fast it's going to go, because you can set those two equal when they trade off their two energies. Or if you just wanted to graph the total energy displacement here, you can get a curve that looks much like what we've seen before with potential energy curves. The potential energy in a spring is 1/2 kx squared, which gives you this parabola, and our amplitudes would be the two turning points. The point where the mass gets as far away as possible and then heads back towards equilibrium. So again, this is a stable equilibrium, and the reason we know it's stable is because if I put a little marble in that little well, that marble will go back and forth from one peak to the next peak and never be able to leave that parabola. So all it's going to do is trade off its potential energy for kinetic energy as we go through our oscillations. That conservative forces like to decrease our potential energy with displacement. So they're the negative derivative of your potential energy curves. What that means is if we have positive slopes for my energy graph, the slope of that will give me a negative force, which means the force is trying to push the mass back towards equilibrium. And if I have negative slopes over here, I'll receive a positive force that's trying to push the mass back towards that equilibrium point. So we can analyze energies, and energy is a nice way to think about where the mass is at different moments in time, rather than having to worry about all the different positions, velocities, and accelerations that an object experiences. Maybe they don't time an oscillation, but you know how far it's been stretched and you know how stiff the spring is. Use energy to analyze where the object is and how fast it might be moving.